As soon as you realize that the derivative of a function is also a function, it makes sense to ask yourself, why not derive that new function again to get a second derivative of my function? And in fact, that's something that has a lot of uses, a lot of practical uses. For example, if f is the position of an object, the derivative of f is the velocity of that object. So it's basically asking how fast is position changing, because derivative is the rate of change. And if you derive again f double prime, whatever this velocity is, it's going to be an expression with respect to x. You just apply the rule. Derive again, that's going to be acceleration. So how fast is velocity changing, right? Makes sense. Actually, you can derive it again. You can find the third derivative, which is called the jerk. So the third derivative of position is the jerk. So it's how fast acceleration is changing, right? You could think if you were driving, for example, you can associate that to how fast you're lowering your foot on the gas pedal or lifting it out of the gas pedal. So that has to do with the jerk, because acceleration is changing when you do that. So out of notation though, just remember that you can keep adding primes near here. So for example, the jerk would be f triple prime of x. That would be the jerk. And eventually you're going to be having too many primes, so replace that with, say, f to the fifth of x. I don't know what that's called in physics, but that's the fifth derivative of position, fifth derivative of x. Okay? So you can also use this, what we call the Leibniz notation. So the fifth derivative is the same as d to the fifth dx5 of x, of f, right? So that's the same thing. So several notations that you can use for higher order derivatives. So how do you calculate higher order derivatives? We're not going to go into the uses and applications of it today, just over how to calculate them. So on each of those examples, we're going to calculate the third derivative of those functions. It's very easy, just a little tedious sometimes. So if you start with the given function, which is f of x equal to 3x cubed minus 5x plus 12, then f prime of x, that equals to, so lower the 3, decrease the power by 1, same thing, and that's 0, so that's f prime of x. So 9x squared minus 5. Okay? So note that this had degree 3 and now derived it once, it decreased to degree 2. So that's the first derivative. The second derivative will be found when I derive this again. So I'll do f double prime of x, that will be the derivative of this. So that will be, bring the 2 down now. So 9 times 2x minus 0, right? Because the derivative of minus 5 is just 0, it's a constant. So f double prime of x equal to 18x. Note again, it was degree 3, degree 2, and now degree 1. So that's the second derivative, but I want the third one. So f triple prime of x will be just the derivative of 18x, which is then 18. So that is now a constant, a degree 0 function. So that is the answer. That's the third derivative of my function. Okay, for a polynomial, that's always going to happen. And if I derived again, that's not what the problem is asking, but if I wanted to, the fourth derivative of x, of f, is 0, because the derivative of 18 is just a constant. So it was degree 3, I derived it 3 times, I got an 18, the fourth time I derived it, the function just disappeared, it became 0. So let's try b. B is saying that y equal to 3t plus 2e to the t. And in that case, I'm going to use Leibniz rule, or the Leibniz notation, not Leibniz rule, the Leibniz notation, excuse me. So instead of using primes, I'll use d dt notation. Note that the variable is t, the independent variable is t and not x. So dy dt is the first derivative, so that's d dt of 3t plus 2e to the t. So then I derive each of them separately, d dt 3 to the t plus d dt 2e to the t. I'm being careful this time. You can pull 3 out. That's d dt of t. So the derivative of t. That's same thing. I can pull the 2 out. Of e to the t. And that will then give me the derivative of t is just 1 because t is playing the role of x. So this is like the derivative of x. And the derivative of e to the t is just e to the t. Just that's the key property in terms of derivatives, the key property of the natural exponential. So that is 3 plus 2 e to the t. So note, this was a degree 1 polynomial. It became a degree 0 polynomial, right? Just a constant. But this was an exponential. It stayed an exponential. Nothing happened to it. So this is the first derivative of y. Now let's do the second derivative, dy, d2y, dt2. So that's the derivative of the first function that I found. So I do the same thing, split it up with using the sum rule. So what's going to happen now is that this derivative is something that I have already calculated. Derivative of 2e to the t. I calculated previously, and I got 2e to the t. So I'll skip some steps, and I'll just get derivative of 3 equals to 0 plus 2e to the t. So then, the second derivative of y equal to 2e to the t. So that's the second derivative. To find the third derivative, I just derive what I just had. So I derive the previous function. And again, that's the same thing I just calculated at the beginning. Right, so that's just 2e to the t. So one curious thing about this is that, so this is the third derivative and this is the answer to the question. So maybe I'll box it, use a different color, huh? So let me box it in blue. Or, sorry, this is not blue, this is black. And I'll box the other one in black, so you know this is the final answer to the problem. So the third derivative of y in that case is 2e to the t. Note that nothing happened to this. So if I were to find the fourth derivative of that, for example, the fourth derivative of y, you'd be right to guess that this is 2e to the t. Doesn't matter what happened, what happens, however many times I derive this, nothing happens to the exponential. So the 100th derivative, even though I'm not able to do that one at a time, the 5th, the 6th, the 7th, I'm not able to do that. The 100th derivative, I know it's 2e to the t. So the exponential, this phenomena of deriving over and over again, what happens to polynomials losing degrees and almost eventually disappearing, is something that I refer to sometimes as killing the polynomial. The polynomial dies after 4 derivatives. It just goes away, becomes 0. But the exponential, so again, this happened to this factor, becomes a 0 eventually, but the exponential factor, exponential term, doesn't ever get changed. It's immune, it's neutral to the derivative. The derivative comes and goes, nothing happens to the exponential. So this is a cool property to remember too, because that helps you sort of have an expectation for other results and other calculations that you may do in calculus.